Hi everyone, so in this video I will be explaining on the neural collapse in deep learning, and the paper is challenge the completeness of this concept right here. It argues that there's still important fine-grained structure in the representations to capture intrinsic structure in the input distribution, and they test it on two dataset, coarse and fine on the CFAR10, but I will be only using the coarse CFAR10, which combine two classes to obtain 5 labels. So in this example, it's shown that there are originally 10 labels, but I'll be combining 2 of them each into one superclass, and there are 2 scenarios that may happen with this, which is the input distribution dominate and the neural collapse dominate. Input distribution dominates, which means that the only one diagonal line here, and neural collapse dominate is 3 diagonal line here. So when input distribution dominate happens, within each superclass in the last layer representation, there are distinguished differences between the original classes, where in the neural collapse is fully collapsed and there's no patterns in the clusters. And yeah, I'll show how I did it. So this is a data processing step. I didn't get 100% accuracy, but 99, 98, I think it shall do. And here's the distance matrix I calculated, and we can see there's a diagonal line here, which shows that our reproduction has input distribution dominate in the last layer representation, and can further be confirmed by t-SNE plots. And we can see that there are clear distinction between the clusters in the t-SNE plots, and we can see that the original classes within this superclass are different. And so in other words, the original classes are distinguished within their superclass. And in the CLP analysis, we can see that the CLP accuracy on the test set is 83%, and the linear probe with the original label accuracy is 95%. So what I did is reconstruct the original train labels and train with features before the t-SNE, or the representation in the last layer before the fully connected layer, and test it with the original labels. There's the original label here is the original data set, so there are 10 labels. And what I found is that mine is a bit lower than the papers. The paper got 93%, where mine is only 83 and 85. So there might be a difference in how we train the learning rate scheduler, the model, the data processing step. Many things are different, where I try to be as close as possible. But we still demonstrate that the neural net still preserve the input structure despite not explicitly required by the training labels. And now I will be experiment on that by adding more data argumentations, and this might somehow boost our accuracy into the similar range as the papers. And I found that the accuracy is boosted, but not as much as the paper. I think we still need to further fine-tuning our model with data augmentation, learning rate, scheduling, and regularization to achieve a closer result to the paper. But I think this is close enough to set as an example on the reproducing this paper. And here's some of my connection to this paper to the things I learned in the unit. So in the unit, I learned more on the theory side, on the concepts, on how to train, how to fine-tune, what happens in overfitting, underfitting, how to deal with them, but not really really challenge the idea or the completeness of such concept as neural collapse. And this paper touches on a really interesting idea on the unique structure of the input, and the neural nets can still learn 5 grain structure regardless of the classification tasks they are given, and highlight an important thing, that how the training data might affect the um, output. And this and we shows that we can still train a model with fewer or coarser labels while still maintaining or capturing a fine-grained structure. And if we think a bit further, the neural nets learn something very fundamental about the input data, not some arbitrary features. And we cannot see this learning like without dimension reduction. We can't really see what's going on. But I think this also explains why transfer learning can transfer to other tasks really well, because it has some sort of intrinsic data structure already. And yeah, that's all there is to it. And thank you for listening.